Welcome, students, to today's lesson in support of exponential functions. We will begin by practicing how to work with negative exponents. In number 1, we have 2 to the exponent of negative 4. We cannot evaluate a negative exponent, but we can make it a positive exponent by moving it to the opposite side of the fraction. Really, this is 2 to the negative 4 over 1, which when I move the 2 down, it will make the exponent positive and leave a 1 in the numerator. This will be how you change the negative exponent to a positive exponent. So when we simplify this, 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 is 16. It is equal to 1/16. Let's practice this again on number 2. We can take and move this 3 to the negative 5 to the bottom of the fraction, making the exponent positive. If I actually evaluate this, 3 to the 5th power is a pretty large number. It's 243. Look at number 3. In this case, your negative exponent is in the bottom of the fraction. Well, to make it positive, we move it to the top. So moving a term from the top to the bottom or the bottom to the top will change the sign of the exponent. So this is now 3 to the positive 2 over 1, or it just equals 9. Let's look at a fraction to a negative exponent. This is quite interesting on number 6. This is a method you might just need to memorize. To make this exponent positive, you take the reciprocal or flip the fraction inside the parentheses, resulting in a positive exponent. To evaluate 3/2 to the 4th power, it is 3 to the 4th power over 2 to the 4th power. 3 to the 4th power is 81, and 2 to the 4th power is 32. Let's look at the exponents of 1/2. Remember that a 1/2 exponent means to take the square root. So number 8 is the square root of 16, which is just 4. Looking at number 9, this is also the square root of 32. Now we can simplify the square root of 32 because remember 32 is simply 16 times 2. And 16 is a perfect square. The square root of 16 would be 4, so this will come out as a 4, leaving the 2 behind, still under the radical. 10 is similar to this. 72 to the 1/2 power is the square root of 72. To simplify this, recall that 72 is 36 times 2. 36 is a perfect square that will come out of the radical because the square root of 36 is 6, but the 2 must remain under the radical. Another important exponent is the exponent of 0. 13, 14, and 15 are very similar, but they're not the same. 4 to the power of 0 is 1, just as 6 to the power of 0, 10 to the power of 0, 235 to the power of 0 would equal 1. Number 14, this negative 4 in parentheses to the power of 0 is 1. Number 15 is a little bit tricky. Negative 4 to the power of 0 has no parentheses, so really this is negative 1 times 4 to the power of 0. Well, 4 to the power of 0 is 1, so this is a negative 1 times 1, so this evaluates to equal negative 1. So be very careful. If there are parentheses, then everything is to the exponent of 0 and it will equal 1. But if there are no parentheses, that negative is not to the power of 0, which will cause a negative result when you simplify this. I believe you will be fine in topic 2 by looking over my handwritten notes. And in topic 3, I'm sure you're already comfortable with this, but we need to review this briefly because you will need these horizontal and vertical lines as you move forward through this chapter. Looking at number 23, it's asking me to graph x equaling negative 2. Remember, when you have only the x variable, this is a vertical line. So here's my vertical line, x equaling -2. Being graphed. I guess I should write on here x equaling -2. And then I'm also going to do a y equals, let's do number 28, y equaling 7. If there's only a y variable, then it will be a horizontal line right here at a y value of 7. Oh, it disappeared. It's kind of hard to get the line dark enough for you to be able to see it. Now, interestingly enough, on number 25 and number 27, when it's x equaling 0, that's actually the name of the y-axis. That is the name of the y-axis, and y equaling 0 is the equation name of the x-axis. Now let's move to percents. You're probably very comfortable with this already, but let's practice it a little bit because you will see this when we have applications in financing. 50% is 0.50. Remember, the point is to the right of the 0 as a percent, which we just assume is there, and we move it to the left 2 places. Looking at number 31, though, this might be a little more difficult because you must remember, regardless of where the point is, you move it left 2 places in order to convert this to a decimal value, resulting in a 0.0008. Let's move down to the connection to college algebra. 3 to the x is an exponential function. The big change here from any prior work you have done in graphing with exponents is that your exponent is now the variable x. This is the new concept that you're learning in this section. So it wants me to complete a table or fill in the table. So if you would like to look at this outside of function notation saying y equaling 3 to the x, if they let x be -2, then your y value would be 3 to the -2 power, which is 1 over 3 to the +2 power, which is 1/9. Here's where the negative exponents come into play. If they give you an exponent of -1, this is 3 to the -1 power, which is 1 over 3 to the +1 power, which is 1/3. If your x value is 0, this is 3 to the power of 0, which equals 1. If your x value is 1, this is 3 to the first power, which is 3. And if your x value is 2, this is y equaling 3 squared, which is 9. So they've given you x values, you calculate the y value, so then you have ordered pair of points that you graph in number 2. So my first point is -2, 1/9. Well, 1/9 is so tiny that it's extremely close to the x-axis, but I will put a dot there. The next is -1, 1/3. Again, extremely close to the x-axis, but I will put a point. 0, 1 is easier to graph. 2, 9 climbs very quickly and is high on the graph. So when you graph an exponential function, you will find that the horizontal x-axis, or the x-axis is your horizontal asymptote. You will not cross it, you will get very close to it or hug it, as some people say. And most exponential graphs will look like the sketch which I just drew. It climbs very quickly when the x values are positive, which is referred to as exponential increase, increasing very quickly. So you do have a horizontal asymptote at y equaling 0, which is the name of the x-axis. You have a domain in which you're going to the far left at -infinity and the far right of +infinity. Your range is that you do not get any lower than a y value of 0. In fact, you never have a y value of 0, but you go up to +infinity. On the next page, you will do something similar by completing the table in which you have 1/3 to the power of x instead of 3 to the power of x. So again, I can rewrite this as y equaling, because sometimes that makes it a little easier. So if my x value is given to be -2, this is 1/3 to the power of -2, which remember is 3 over 1 to the power of +2. So this is 3 squared, or 9. If my x value is -1, 1/3 to the -1 power is 3 over 1 to the +1 power, which is 3 to the first power, which is 3. If my x value is 0, remember when you take something to the power of 0, it equals 1. So you should consistently, through your exponential equations, unless they're being transformed by moving them up or down, you should have the point 0.01 on pretty much every exponential function. If my x value is 1, this becomes easier. 1/3 to the power of 1 is just 1/3. And an x value of 2 is 1/3 to the power of 2, which is 1 squared over 3 squared, which is 9, so it's 1/9. This graph is going to look different because your base was a fraction. Instead of being 3 to the x, you have 1/3 to the x. When you graph this one, you will continue to have a horizontal asymptote, which is the x-axis. But when I plot these points, kind of hard to get on this graph, but I'm at -2, 9, I'm high on the left side now. -1, 3, 0, 1, and 1, 1/3, and 2, 1/9. Your graph looks a little different. Instead of exponentially increasing, this is exponentially decreasing. It's dropping very quickly. So this function will always be going down or will always be decreasing. So when you have a fraction to the power of x, a third, a fourth, a fifth, a seventh, a tenth, your graph will go down instead of up. It will be always decreasing. You will continue to have a horizontal asymptote, which is the x-axis, named y equaling 0. Your domain will continue to be from -infinity to +infinity, and your range will continue to be from 0 to infinity. But just remember, if it's a fraction to the power of x, it is exponentially decreasing, not exponentially increasing. This is a financial question, number 5. It says Bethany needs to borrow $10,000, and she can borrow it at 5.5% simple interest for a time period of 4 years. Now, your simple interest is going to be labeled as R, and you must take that percent and change it to a decimal value, which is why we practice percents to decimals. Simple interest is a formula I equaling P times R times T. P is the original amount of money, T is time in years. So your interest would be your principal of $10,000, your interest rate of 0.055 as a decimal, and your time of 4 years. This is going to be your interest amount. Interest is the amount of money that she's going to owe the bank in addition to the $10,000 because they permitted her, or they took the risk of permitting her to take that money from the bank over a period of 4 years. So what she's going to owe the bank on top of her original $10,000 is interest, which is $2,200. So in other words, she took out a loan for $10,000, and she also owes the bank $2,200 in interest. So this means she's going to owe the bank $12,200 at the end of 4 years. The interest amount is the $2,200. Part B is a little different. They've changed the interest rate to 5%, and they now say this is compounded continuously. The minute you see the continuous compounding, this is a new formula, which is A equaling P times e to the power of RT. So your P remains the $10,000. Your R, they changed it from 5.5% to 5%, which is your 0.05, and they maintained a time of 4 years. You want to evaluate your exponent value, so you want to take your 0.05 times your 4 first, which is a 0.2. On your calculator, you must evaluate e to the 0.2 before you multiply it times the 10,000. And this is going to be a long decimal value with a lot of digits in it, so you want to hold it in the calculator after you've come up with that value, and then last but not least, multiply it times 10,000. When you do this, the result is 12,214.03. So the amount she owes the bank is the 10,000 original dollars that she borrowed plus interest, which totaled out to be 12,214. So the better option for her would be part A, where she pays a total of 12,200 versus part B, which is 12,214.03. This is the end of this recording. Have a great day.